Let's just continue with AR6 here. So we looked at the soil moisture and rainfall and so on. Let's look at projected changes in extremes. As the statement reads, this is summary for policymakers, so they are often put as statements. So projected changes in extremes are larger in frequency and intensity with every additional increment of global warming. So these statements are now becoming more confident in the science and in attribution, even though we saw that there are many places where the confidence in attributing to human contributions is not that high when it comes to rainfall, for example. Hot temperature extremes over land. So the new thing here is that we are looking at 10-year event and 50-year event. Remember, I mentioned before that we have return periods in the natural climate, and we want to see how global warming modulates the return periods, or how it loads the dice, as we said, right? So frequency and increase in intensity of extreme temperature events that occurred once in 10 years on average in a climate without human influence. Okay, how are they going to change? So here we are looking at frequency per 10 years and intensity increase. So 1850 to 1900, where human influence was quite minimal, once in a 10-year event, of course, occurred once in 10 years. At present, we have already warmed by a degree. So now likely occurs 2.8 times, with the confidence interval going from 1.8 times to 3.2 times. So this is kind of the global average picture, and the intensity has become plus 1.2 degrees C, so it's gotten hotter. So the events are not only occurring more often, but they are also beginning to be more intense. Future warming levels, 1.5 degrees C, they will likely occur 4.1 times in 10-year events. So 2 degrees C, it'll go to 5.6 times, 4 degrees C, it'll go to 9.4 times. Okay, so intensity, of course, will go to 1.9 degrees C, 2.6, and 5.1 degrees C. So return periods are changing, intensity of the extreme temperature events are changing as well. Okay, a 50-year event, frequency and an increase in intensity of extreme temperature event that occurred once in 50 years on average in a climate without human influence during 1850 to 1900 is already occurring 4.8 times instead of just once in 10 years. So that's and it's 1.2 degrees C hotter compared to the to the period where human influence was minimal. And there are many examples now, heat wave, not only in countries like India and China, but also in Europe, in the Soviet Union, that happened in, or Russia, that happened in 2010. Europe was 2003. They got shocked by I think almost 75,000 people dying from a warm heat wave. Okay, future projections: 1.5 degrees C warming will lead to 8.6 times the occurrence of the events, with 2 degrees C warmer intensity. Under 2 degrees C, it will go to 13.9 times, and under 4 degrees C, it will go to 39.2 times. So the frequency of a 10-year event or a 50-year event would jump by 39.2 times. So it will be more intense by 5.3 degrees centigrade. Okay, so just imagine how worse it's going to get. Temperature response is rather direct, but when you look at heavy precipitation over land, 10-year event which occurred once in the 1850 to 1900 period, under 1 degree C warming, it is now occurring likely 1.3 times, with plus 6.7% wetter intensity of heavy precipitation on land. Will likely occur 1.5 times, 1.7 times, and 2.7 times in the warming scenarios of 1.5, 2, and 4 degree centigrade, with 10.5% wetter, 14%, and 30.2% wetter. 30.2% wetter. 2021 summer was a monster year in season in extreme events. The flooding in Europe, flooding in China, Japan, India, US, it's just been a poster child for extreme events this year. And as I said, despite the La Nina, it's been really warm as well, and probably will end up again being one of the warmest years. Not sure where it will rank, but it'll rank pretty high. Agricultural and ecological droughts in drying regions, so look more specifically at the drying regions. They have gone from once in 10 years to 1.7 times, will occur 2 times, 2.4 times, and 4.1 times in future global warming levels of 1.52 and 4 degrees C warming respectively, with standard deviation being 0.3 standard deviation drier, 0.5 standard deviation drier, 0.6 and 1 standard deviation drier compared to the base case of 1850 to 1900. So this is a better way of to think of the risks, whether it comes to cyclones or heat waves or heavy precipitation events or agricultural and ecological droughts. People have a better sense of this kind of probability of occurrence of events. Many times we say a rainfall was once in a 1,000-year event. That doesn't mean we have 1,000 years of data. There are ways to use the long time series we have to create statistically the return periods based on the amounts of rainfalls. So let's look at some CO2 sinks. The proportion of CO2 emissions taken up by land and ocean carbon sink is smaller in scenarios with higher cumulative CO2 emissions because the carbon uptake is going to be saturated in all of the sinks that we know of. So here we are looking at gigaton CO2. Total cumulative CO2 emissions taken up by land and oceans in colors and remaining in the atmosphere in gray under 5 illustrative scenarios from 1850 to 2100. So we are going here from SSP1 1.9 2.6 to SSP2 4.5, SSP3 7, and SSP5 8.5. So these are combining the various governance issues, rapid changes, mitigation difficulties, adaptation difficulties or challenges, and radiative forcing. So things have gotten complicated, but you know what they mean. So here we are looking at future scenarios with higher cumulative CO2 emissions, amount of CO2 emissions taken up by land and oceans. Carbon sinks is larger, but more of the emitted CO2 remains in the atmosphere. This means that the proportion of CO2 emissions taken up by land and ocean carbon sinks from the atmosphere is smaller in scenarios with higher CO2 emissions. So the land and ocean will continue to take up carbon dioxide as the concentrations increase, especially cumulative CO2, but they will take up less and less of the total proportion of cumulative CO2. So the accumulated atmospheric CO2 will increase, which is obviously a clear indicator of increased global warming as well. It's not hidden away in land and ocean. It remains in the atmosphere, then it directly contributes to trapping long-wave radiation and warming. So here under the benign scenario, land and ocean will take up 70% and atmosphere will keep 30%. It'll drop to 65% under this scenario, 54% here, 44 and 34. So you can see that the proportion of what remains in the atmosphere increases very rapidly, and the increase in the land and ocean box gets proportionately smaller and smaller as the cumulative CO2 goes up. So this is expected because the ability of the land and oceans to take up CO2 cannot move as fast as we can emit CO2. because there are, as we saw, the carbon cycle, and especially on land, the amount of CO2 that can be pushed into the soil or wetlands, etc., is not as fast. Ocean is relatively faster, but still it cannot keep up with this increase. Plus, of course, there is also the acidification, which is not being part of this calculation here. So human activities affect all the major climate system components, with some responding over decades and others over centuries. So global surface temperature change relative to 1850 to 1900. These are the scenarios we talked about. So we are in the range of maximum warming here with SSP 5 and radiative forcing of 8.5. So that's a combination of scenarios there of RCP and SSP. The September Arctic ice extent is expected to keep dropping. There is some flattening or maybe a recovery under the benign scenarios, but the worst of the scenarios will practically make it ice-free by about 2050 or so. A little bit later if you reduce it by from 8.5 to 7 and SSP 5 to SSP 3. Global ocean pH, of course, a measure of acidification, is going to get worse and worse. So we are at 8.1 already in 1950. This is already somewhat acidified compared to the pre-industrial levels, and it's going to drop pretty dramatically down to 7.65 or so if under SSP 5 8.5. The cascades into the ecosystems is going to be quite dramatic in terms of coral losses and losses of many of the calcifiers that we talked about, forams, coccolithophores, and so on. Global mean sea level change. There is one low likelihood high impact storyline, including ice sheet instability under SSP 5 8.5, which would lead to sea level rise global mean of more than 1.5 meter by 2100, but the rest are here under 1 meter. And of course local sea level rise is going to matter a lot as well. So even under the most benign scenario here, we can expect more than 50 centimeters of sea level rise by 2100, and there are some models indicating that we may be underestimating that. So here is another way to look at it. SSP 1 2.6 is down here. So this is global mean sea level change in 2300 relative to 1900. So with accumulated carbon and committed warming, even if we stick to these benign scenarios, cumulative carbon will continue to warm the temperatures, melt the glaciers, expand the oceans, thermospheric sea level rise, and so on. So you can see that in the worst case scenario we could get as high as 7 meters, with possibilities of reaching 15 meters that cannot be ruled out by 2300. But again, uncertainties remain high here. So let me stop this podcast here and come back and add some more points from the AR6 projections. The book has only CMIP 5, but by the time I'm recording this, AR6 is out, so I'm just including it. And AR6 does things a little bit different than CMIP 5, so I'm just including whatever is made available in the summary for policymakers by AR6. Okay.